Good afternoon and welcome to this week's Webinar Wednesday. We're excited that you could join us, and we're even more excited that we had nearly 300 people register for today's presentation. As always, just a quick reminder that today's presentation is eligible for 1 CE credit from the ACI. But we want to get started by giving you, our attendees, a chance to win. This week, a Webinar Wednesday surprise pack will go to the first attendee that can answer our trivia question correctly. Today's sponsor, Technical Prospects, is headquartered in Wisconsin. What is the name of Wisconsin's oldest city? You can answer now using the question feature on your dashboard. And while you're answering, I want to invite you to join us for our 5th annual Imaging Conference and Expo. It's going to be held this year in February 16 to 18 at the M Resort Spa and Casino in Las Vegas, Nevada. The ICE conference brings imaging service professionals from across the nation to Vegas for 2 days of learning, networking, and the latest advances in imaging technology. Registration is open. You can find additional details on the conference and how to attend for free by visiting attendice.com. All right, let's see who our lucky winner this week is. Congratulations to Nathan Bassett. You're the winner of this week's Webinar Wednesday surprise pack because you knew that the oldest city was Green Bay. Webinar Wednesday would like to thank our sponsor, Technical Prospects. Technical Prospects is your only alternative to new, pre-owned, and refurbished Siemens medical imaging parts. Also offering engineer training on your Siemens medical imaging equipment and technical support on your parts purchases. Technical Prospects is your partner at every stage. You can learn more about today's sponsor by visiting their website, technicalprospects.com. Our presenter today is John DePasquale, Technical Trainer and Support Specialist at Technical Prospects. He is a certified biomedical equipment technician and has over 25 years of experience in the HTM industry. John, you may begin whenever you're ready.
Thank you, Jamie, and welcome, TechNation, to Imaging from Film to Digital. Before we get started, a little bit about me. I got my start in the U.S. Air Force, where I served initially as an aircraft electrician for 4 years, and then I retrained into the world of biomedical equipment. I spent the balance of my career, the 18 years, as both technician, manager, regional manager is how I ended it, but I also spent a number of years as an instructor in the Air Force. After my military time, I spent 8 years in various imaging and biomedical capacities, including asset management for both in-house and third-party contract positions. In late 1999, I left the industry for about 7 years, and I hooked up with the Connecticut Vocational High School system, where I taught high school mathematics. After 7 wonderful years there, I came back to the industry in 2006 and hooked up with Hologic, who was my first OEM experience. There, in addition to technical support, I took on the role of technical trainer for both their analog and digital imaging systems and support system for their various mammography lines. In 2013, I left Hologic, moved to Wisconsin, and later that year, I began my career here with Technical Prospects. My education and credentials includes a master's degree in education from Boston University. From Wayland Baptist, I have a dual bachelor's in electronics engineering and business administration. I have 2 associate degrees, one in instructor technology and the other in biomedical equipment. I've been a CBET since 1994, and during my time in the Air Force, I was recognized as one of their master instructors. Anyway, enough about me. Let's take a look at what we're going to cover. As our title suggested, from film to digital, we're going to look at all different forms of imaging. We're going to start with film. We'll move into the world of image intensifiers. We'll look at the various aspects of digital imaging. And lastly, we'll get into some troubleshooting tips and tricks. So let's begin with film imaging. Here we're going to take a look at some construction, the intensifying screens, and also film processing itself. When we look at the construction of film, the biggest thing that we need to realize is that there was basically two categories of film. The oldest being direct exposure, and the one that is used when we have a lot of detail. But the most common today is one that is screen sensitive, which, and by that we talk about light sensitive. This is our most common. These film exist in two different types. We have single emulsion film, which is predominantly used in the world of mammography and or when the technologist needs a high detailed image. For general radiography, our film is double emulsified. In this case, we have emulsion on both sides. So in looking at that, when we look at the construction of our film, you can see from the picture that there's various layers that make it up. The most common is the base and also the most thickest. Then we have the adhesive where we use some glue to hold the emulsion in place. Now this is the key part. This is where the different sized silver halide crystals are, and we also have the light absorbing dye to help focus our light coming off of the emulsion portion. In order to protect it, we put a super coat on there, and the super coat is very critical because this allows for both processing and chemical reactions to take place in the emulsion, as it allows the chemicals to seep through into the emulsion and work on the silver halide crystals. Moving on here, the biggest advancement though was the intensifying screens. And here we look at the composition of the intensifying screens that are made up of a base layer, a reflective layer, the heart and soul, the phosphor layer, and lastly, a protective coating. Now the phosphor layer, the biggest thing here is this is what's going to set up the screen speed. All right, this is dependent upon the size of the crystals. Now, as time has gone on, the crystals today are more uniform because we use more of a man-made type crystal. However, back in the early days, we used chunks of crystals and they were different sizes and stuff. So this would also determine the amount of light being emitted from the screen. The thickness of the phosphor layer, obviously that determines how many crystals could be inside the layer, but also the different sizes. And lastly, the dye surrounding these crystals. What we need to do is ensure that the dye helps us put light directly straight out to the film and not create a diffusion aspect, because we know from our study of physics early on that light travels in 360 degrees, but we need to focus it and have it go straight to our film, at least as much as possible. The biggest thing that we need to look at here is the inverse relationship, because image quality will decrease as speed increases. If you think of this way back when, for those of you who remember the days of single lens reflex cameras, you had different film speeds. And based on the different film speeds, our shutters would then open and close at different rates. Our faster film speeds allowed us to capture and freeze images, but our colors were not as rich and as vibrant. Conversely, when we had the slower film speeds, we could get good, beautiful, rich color. However, our shutters would be open longer, and then if there was any movement, we would lose the quality of the image due to blurring. The biggest thing that we need to recognize here about the screens is they exist in three different types: fast, medium, and slow. And this also is used to match the different speeds of film. The biggest thing here, when back in the day when we used a lot of film, we had something known as screen film combinations. A medium speed screen with medium film would be one combination. A medium speed screen with fast film would be a second combination. Our earlier X-ray machines required us to do different levels of calibration based on these screen film combinations. And that's why it was extremely critical to know what type of screens and film speeds so we can keep them as matched as much as possible. Moving on, looking at processing here, there are basically two types of processing factors that are used, with film. One is manual, where they do all the work, and that's how we started out years ago. However, the advent of automatic processors made it much better for us. There we had 90-second film processing, and in some cases I've seen them as fast as 45 seconds. When we looked at the processing, though, there were four basic stages and main stages that we went through. This was the developer. Then here we had solution that adhered to the charged silver halide crystals that were exposed by the light or X-rays, depending on the type of film. The biggest thing with developer, though, is that it was very, very temperature critical. That if we were too high or too low, it would definitely affect the quality of our image. Our second stage was the fixer. This accomplished two major things. One, it removed the uncharged silver halide crystals from the film, but the ones that were exposed were fixed to a level of degree of blackness so that it wouldn't change. Moving on from the fixer, we then moved it to the rinse and wash stage where we took the chemicals off of the film. And after a period of time in the wash, we then sent it over to the dryer, which then permitted us to safely handle the film without any type of damage. Now, looking at this, we found that there were four key systems involved in film processors. The biggest one was the transport, because this moved the film through the different stages of the processing cycle. The crossover, which was a part of the transport, all right, the biggest thing here is it used a squeegee action to prevent cross-contamination of the chemicals as it moved from one stage into the other. This could compromise the chemicals, and that would make a great deal of work for the appropriate field engineer out there in the field. Replenishment was a major system to us, as every time we processed a piece of film, we took some of the chemical with us, and that reduced the strength of the chemical. So based on the size of the film, our automatic processors would activate a replenishment pump that would go into our chemicals and replenish the different chemicals to maintain the strength, which would help us ensure the proper processing of the film. And as we stated earlier, temperature being a critical factor, we predominantly had temperature in two areas of our process. One was in the developer, where it was extremely critical, and lastly was the dryer, so that we could properly dry the film to ensure our safe handling. Moving on from film imaging, we're going to move next into our world of image intensifiers. All right, we're going to look at a little bit of history here, talk about the construction of the image intensifier, some principles of operation. We're going to look at some external factors and components that affect the operation, and lastly, the types of recordings that are possible due to this advancement. Looking at the history of image intensifiers, here is some of the very, very early days, as you can see by the couple of images. In the one image where it talks about direct fluoroscopy, where it's obsolete, you can see where the X-ray tube is shooting from the posterior to the anterior through a patient into an imaging screen, and the radiologist is sitting directly behind the screen looking at the X-ray. I think we can all see why today this was kind of an obsolete measure here, because the radiologist was directly in the beam. And then in the picture directly next to it, you can see an early surgery procedure where you see the exposed high voltage tank and X-ray tube right there by the radiologist, but you see something over his head. That was known as the fluoroscope. And what this did is that replaced that big fluoroscopic screen over here. However, again, the radiologist is again looking directly into the beam on the fluoroscope, where he can now see the image of the patient. Moving on from here, you saw the advancement of the image intensifier tube, and this occurred in the early 1940s. All right, in this picture that's directly below this, you can see now where the radiologist is off to the side and out of the primary beam. This was a major advancement. Now, what you can't see here too clearly in the picture, but this is back in the days when I first got my start here in imaging, that image intensifier had a series of mirror optics over there, and the mirror would then take the beam coming off of the image intensifier, direct it to a mirror, and the radiologist is actually looking at the green light coming off of the image intensifier on a mirror, seeing what is going on with the patient. As you can see, that we've moved on even further from that. In the 1970s, we used some camera pickup tubes that allowed for additional recording devices. It brought about the CRTs. In the picture here, you've seen we've even advanced further. We no longer use CRTs. We're now using flat screen monitors. We have multiple monitors. We're using CCD cameras, and there's been all sorts of major advancements that have happened in our world of imaging. But moving on, when we look at the construction of the image intensifier, you've got a great picture here that shows you the vacuum tube. It shows you the input screen at the very bottom where the x-rays come in, and we use the input screen, which is like a phosphorescent layer, that we take the phosphor and this converts the x-rays to light energy. This is then picked up by the photocathode, and the photocathode takes the light energy and converts it into electronic energy. The acceleration plates that you see along the side of the vacuum envelope, this here is what's going to accelerate our electrons, and they're going to blast the output screen at the very top. This screen should be much brighter than the input as it's condensed, smaller, and you now have the whole image placed at the very top of the intensifying screen. In looking at the principle of operation here, that acceleration of these electrons due to the high voltage will generally make the output of our top output screen at least 9 times brighter than the overall input screen. The circuitry also allows for various focal points to permit magnification. Depending on the type of system you have, you can have anywhere from 1, 2, or 3 different levels of magnification, where we actually take less of the image from the input phosphor, and we spread that smaller image across the whole output screen, therefore magnifying our image that we input. The phosphor here, again, we said it converts the X-ray to electron energy, and the output converts the electron energy back to light energy. From there, we have our mirror optics assemblies, where we can direct the light coming off of the image intensifier to different devices, whether it's a video camera, CCD camera, a video tube. We can direct it off to different other cameras, and we do a lot of different things with that image coming off of the intensifier. Some factors that we can look at that will, and components that affect the operation externally, the biggest one is the max R output from the tube. This is ensuring the proper dose. This is something that you as field engineers need to ensure that we have the proper dose coming into the image intensifier. The second thing that you can do that's very important to the image intensifier are the proper voltage to the acceleration plates that are within the tube. Now, you need to be highly careful here because this is very high voltage. The image intensifier will typically have upwards of 30,000 volts on that last acceleration plate. What a lot of manufacturers do is they build in a voltage divider for you to test the different voltages on the side of the modern day image intensifier. This is something you should be looking at every PM to ensure good image quality. Another factor to think about here is the proper light coming out of the image intensifier going to the camera or pickup tube through the iris. Now, our iris here is going to be responding typically based on the first pulse of X-ray coming in. It's going to open up and set the typical amount of light from that particular standpoint. As we go through our operation of the fluoro exam on our patient, as we go through different body parts, we're going to see changes in light output of the image intensifier. Here, we will use either photomultiplier tubes on older circuits or photodiode arrays on your more modern systems here to sense the light changes that are coming out of the image intensifier, which will then trigger a change in both the auto KV or possibly even the output dose of our X-ray tube to compensate so that we can maintain our good quality image quality coming off of our image intensifier. Now, with these outputs, we did all sorts of different recordings and stuff. The biggest one that was possible, we can thank our lawyers for, and that was something called spot film. What was going on, if you think about the overall operation of a fluoro exam, these were performed by the radiologist by themselves in the room, and they're seeing what's going on in the patient. Well, like anything else, how do I know what you saw, doc? Where's your proof? So what the industry did is they came up with a device called the spot film device. And back in the day, this was an absolute electromechanical nightmare. And for those of you who remember them, let me just give you a little blessing. But basically, what we did here is at the quick turn of a handle, our generator stopped the fluoro operation, converted to a radiographic operation, and was going to generate a high MA shot across our patient to expose a piece of film. We had a piece of film back in the tray that we would then bring forward into the beam. We would collimate down based on the programming of anywhere from 1-on-1 to 16-on-1 exposures on a piece of film. And we would collimate and put our image on the piece of film, making a radiograph that had to be photo timed because we didn't know where in the body it was going to be required, so that we could get a good quality image, as we only got one shot to get this correct. At the end of the radiograph, we would then take the film, send it back into the holding place. Our generator would then leave the radiographic mode and go back into fluoro. We would then accelerate. We would then have the X-ray start coming out of the tube at a much lower rate, and then now start using the image intensifier to again begin our fluoro exam. I think you can kind of see from that explanation why I call this an electromechanical nightmare, because all between the different mechanics, the changes in calibration, we spent a lot of time repairing this particular system. Some other factors that we had were cut film devices where we used sheets of films, and we used radiographic exposures using different frame rates. An early example of another camera that was used in the day was something called a cine camera. Here we used roll film that would be sitting and mounted on a camera, and we had a variable frame rate anywhere from 15 to 120 frames per second, where we would be flipping through and making x-rays and pulse the fluoro exam or pulse the fluoro beam at a higher MA in order to expose this film, and we would create a motion picture. Of course, the hard part was developing that roll of film and then hoping that we got everything good. Fortunately for us, as technology improved, came the beautiful, wonderful VCR. And here we were able to recorded a live image of what was being sent to the monitors, and that kind of helped replace the cine camera. It also made it easier for us to process and gave us better quality image. Now, this was the early days of possible recordings. Let's take a look now at the evolution as we go into the world of digital imaging. Here in the world of digital imaging, we're going to look at some devices that are used, talk a little bit more in detail about CR, talk about the flat panel detectors, the construction of them, some principles of operation. We'll look at some external factors and components that affect the operation, and also the changes in the recordings that are possible. Here in the world of our devices used, there's your CR cassettes. You may see these. As you can see, they replaced the old analog film cassettes. They come in different sizes, and this was a low-cost change into the world of digital. Another factor that changed was CCD cameras. as we replace the old tube technology with our CCD cameras, and you can see this is one example of a picture with a built-in iris as it exposes our CCD chip. The third factor here are arrays and detectors, and here I show you a picture of a portable type array. Some arrays today are still add-ons to systems where we move up into a digital world that way, or we also have detectors that are now built into systems, and as technology has evolved, we've now gone back to portable detectors that are now battery powered. So these are the different types of devices you're going to see here used in our world of digital imaging. Starting off at cassettes, as I alluded to earlier, this was the low-cost upgrade to the digital world from the analog film. It required two components, that of a CR cassette and a CR reader. Now the cassette basically here had its composition, and here you can see the cross section of the CR plate. You have the backing layer, the base, the anti-halo reflective layer, the key one being the phosphor layer, because the phosphor held the image that it received from the light from the intensifying screen that is part of the CR cassette. And then you had a protective layer that was used to protect the overall phosphor. When we looked at the principles of operation, here you can see where the X-ray tube is exposing the cassette with the storage phosphor. All right, the screen converts our X-rays to light. It will then take the light, the light image is stored in the phosphor, and here we're going to send it to our reader. Now, the key thing here with the reader is it needs a minimum readability value, and this is known as the S-curve. For those of you who remember the world of film, I kind of liken this to the world of optical density in our film world, which refer to the degree of blackness. This S-curve is the minimum value needed for the CR reader to read our CR cassette. Once we've achieved that minimum value, we have the laser that goes inside through the mirror and scans our storage phosphor. All right. This excited storage phosphor now is being read by the photomultiplier tube, which takes this and sends it to the computer for processing, and our computer program then is what compiles our image. While that is going on, in order to reuse the cassette, we're going to send the cassette and we're going to expose it to intense white light, which basically neutralizes the plate and prepares it for the next level of exposure. And that will then allow us to then reuse the cassette moving on. Moving on from CR, let's take a look at some arrays and detectors. Here, when we look at this, we're looking at various types of flat panels. When you look at the direct conversion, which is shown in the picture there, you see it uses a selenium plate, and here the X-rays are converted directly to an electrical charge through the selenium. When we use the indirect conversion, which is to the right of the direct conversion, you see you have two different types. One uses a scintillator, which will convert the X-ray to light energy and will go through photodiodes and then charge our transistors, or we'll send it from the scintillator directly to a CCD camera. All right. And as you can see that we have two different types. We can have transistor type detectors or CCD camera detectors. And again, this is strictly dependent by the design of the system that you're servicing. From here, when we look at the construction of flat panels, all right, we notice we have two different types. You have direct and indirect. And if you liken this to the world of film, we talked about direct exposure film and light exposed film. This is basically the same thing that we're looking at here in flat panels. So the panels are just an outgrowth of our film industry. When we look at the principles of operation here, again, you see both illustrated in the picture with the indirect being on the left and the direct being on the right. If you look at the indirect, here we're taking the light from the phosphor to activate the photodiodes. that when conducting, establish different levels of charge on the capacitors, which will affect the level of conduction of the transistors. All right? This charge is what helps us determine the different shades of gray that are being sensed by our detectors. In the direct type of flat panel, here we use selenium material, which will directly charge or change the X-ray beam to an electron, which will then, based on the quantity of electrons, charges the storage capacitor for the transistors, which will affect the level of conduction for that cell and hence the degree of blackness. Two different ways of accomplishing the same thing, but you need to ensure you have the correct detector for your system. Now, when we look at external factors, let's look at what's happening with the operation here. A couple of key things are proper supply voltages. As we lower voltages and lower voltages throughout our systems, grounding or circuit reference becomes even more critical, because grounding, if they're not properly torqued and set, can induce additional resistance, which will then change our ability of our circuits to properly respond. Some other factors that will affect the operation, the biggest one is temperature. For those of us that have played with these digital detectors out there in the world, when you get a brand new one, it tells you got to let it sit for 12 to 24 hours while it gets used to the ambient temperature. You know, we all know that the technicians want us to get in there and just do it right away. We can't, because we have to allow for the ambient temperature, it to get used to its environment. The other thing that some manufacturers are doing is they're holding off and forcing it to be in an operational mode, be at an operational temperature before it allows you to even do the calibration. So both of these temperatures are something that you need to be aware of and comply with in order to ensure that our detectors will give us the proper output. This is going to look at detectors and CCD cameras. Now, let me explain something about the CCD cameras. In one of my former lives, we actually had one that operated at minus 23 degrees centigrade. Putting this camera on, there was a 10-minute wait period before the operators were allowed to do anything. And that was helped us to ensure that we would get good quality images. Hence this temperature factor that we talk about. With detectors, we have operating ranges that they have to be in. We need to ensure that they're there. Some other external factors are software files. Of these files here, I'm really going to emphasize two: your map files and your calibration files. One, you need to ensure that the map file is proper for either your camera or the detector. Map files are typically ones that identify defective pixels at the time of manufacture. Okay, calibration files are ones that do updates and also give us different levels of calibration. So these files here, which designed by the manufacturer, are put into this, are used by the processing software to ensure that we get good quality images and they can compensate for what is known to be defective. Some external components that affect the operation. Okay, we have talked about this before. The input to the detector, the X-ray tube output, kV, MA, dose, in millirankins or rankins. Is that all proper? Collimation. Are we properly collimating it down to get what we're looking for? And also removing scatter radiation, which will also destroy good image quality. The other thing to talk about here is the output of the detector. The iris, is it allowing enough light going to either the camera or the photo tube, depending on what you have? Mirror optics, is it properly directing the light to the appropriate device? Our recording devices, these all use low output signals in the digital world. Are we getting the appropriate factor? And then when we're in fluoro, we talked about this earlier, the auto correction circuit of either a photomultiplier tube or the PDA, the photodiode array, which is the most common today. One of the things that I would suggest to you is when you're doing your PMs out there, put different density material and make sure that this make sure that this auto KV correction circuit works and works quickly. When we look at viewings and recordings, some of the things that you now see more common today in our world of digital imaging. One, monitors. Radiographics are static images. Fluoroscopic or live images. And when you get to some of these more sophisticated systems today, you'll have one monitor showing you the live image, and then you'll have the other monitor showing you the image captured or the radiographic image of what they just took and made a recording of. DVRs replaced our VCRs. This is, again, a low output recording of the digital image from the computer. Spot film. This was the big change as far as what the digital world brought for us. If you think about your little camera phones or your portable digital cameras you have today, you can see what's going on, and when you press a button, it captures that image. We do the same thing here in spot film. The biggest change was no increased dose to the patient because we just captured that low-level fluoroscopic image, made an image capture, stored it off on the side for viewing later or printing on film or whatever they wanted to do with it. But again, this was the proof of what the radiologist saw during the exam. Another thing that's come about here was digital pulse fluoro. All right, here this is a higher dose output than normal fluoro. It's similar in nature to the old cine mode where we used roll film. However, with its variable rate, we can also record this on a DVR. The biggest problem here is it's a higher level dose rate to the patient whenever they go into the digital pulse fluoro. Moving on from digital, let's get into our final topic of this presentation today, and that is troubleshooting. Things that we can do as field engineers out there to help us isolate and figure out what's going on. We're going to talk about circuit isolation, a little bit about the imaging circuit, some tips, and some things to think about. When we look at isolation, I'm looking at predominantly, is the problem in the generator or is the problem in the imaging section? A couple of devices that I think that can make this easy for you would take a fluorescent screen. Now, if you don't have an old cassette laying around, if you do, just cut it out of there because all we need it to do is just glow. Get your KV meter and get your MA and mass meter. And if need be, you can add your dose meter into this as well. What I want you to do is to generate an X-ray. Look at the outputs. Does your screen glow? It means you're making X-rays. Check your KV. If it's at the proper amount, we're good to go. If MA and mass is proper, again, we're good to go. If dose is good, your generator's fine. Now our problem's on the imaging side of the house. Look at what we just did. In one quick X-ray, we can determine which side of the house our problem is on. When we look at the imaging circuit for radiographic, let's start over here with film. We're going to look at the discrete components with specified functions that all affect a piece of film along the way. The cassette with the film, all right? Have we got light leaks? That creates dark edges. That's not good. How about the dark room itself? Is the safe light good? Is our storage good? Are we getting leaks inside there? Are we exposing it to chemicals? That can create a chemical fog on the film. Our film processor itself. There's supposed to be a daily QC done on the film processor by the operators. And that's supposed to be within a specified range. If you have an image quality issue, one of the things that first thing I would do is take and run a film through that film processor and see if our processing has changed and is now outside the QC range. If it is, my problem's in the processor. It's not in my imaging chain, not in the other part of the imaging chain. Also, our viewing lights. Are we getting the proper amount of light on the light boxes? This is something that should be checked on PMs. And back in the older days, we had hot lights that were really intense lights to help us see even more clearly. The end result of all of this is that the film image must be clear enough to read and allow for proper diagnosis. If it's not, we got to do retakes. In the world of digital, again, we're going to look at the components that make up the electronic file. We're going to start here with the detector or camera. All right. Here, we're taking it, we're getting something with the x-rays. We're going to send it to a computer program to assimilate the information and create the file. And then we're going to put that file on a monitor. Now, the nice part about this is I get to play with that a little bit to see what's going on. But again, the key factors here are these three components here may help make up the basic image that is presented that we can electronically adjust for viewing and diagnosis. When we look at the fluoroscopic circuit, let's start with the analog side. You've got a lot more components. First off, you got your image intensifier tube. Is it properly functioning? You have the mirror optics, which is going to direct the output light somewhere. You have your photomultiplier tube. That's going to be in between the output of the image intensifier and whatever recording device that we're going to be using, because that's going to be monitoring the light. And that's going to help set up and trigger our auto KV circuit. The iris going to our photo tube. All right, this is controlling the amount based on the opening and closing of the iris. All right, the iris itself may or not be part of the auto KV circuit, depending upon individual design. We have your photo tubes, your Plumicon, Vidicons. Well, we don't have Radio Shacks out there anymore with tube testers. So tubes aged. As they aged, our output became diminished. This was a quick fix years ago. Not so much today. And lastly, we had our monitors and recording devices. Now we were really, back in the day, we were worried about scan rates and refresh rates and compatibility and various signals and blanking signals and interlay scans. All sorts of different things that were part of the imaging circuit that we had to concern ourselves with. In our digital world, you can see we have a whole bunch of different components. We've moved on from the image intensifier to a flat panel detector. We still may have mirror optics determining where that output is going to go. And now we use the photodiode array, a little bit more sensitive than the photomultiplier tube. We have irises now that control the amount of light to the various devices and stuff, or to our camera, such as the CCD camera. All right. Now, CCD cameras come in different pixel sizes, and that's going to help, again, determine the quality of our X-ray that we're looking at. We take the signal that's received by the CCD camera, and we send it off to a computer for image compilation. Then we send that compiled image to our monitor or recording device, and this typically uses a low resolution. What I'm talking about here is a 14-bit versus a 12-bit signal. Looking at some tips for fluoroscopic. All right, we talked about it earlier. Check the power supply voltage of the detectors in the IIs. If these are correct, that's the important thing in terms of making sure that these devices are working correctly. If you can physically verify the light output of the detector or our II, that's great. Little tip when you do this though, completely darken your room. All right, because otherwise you're going to be affecting other parts of the circuit when you remove the cover, so because you don't want to expose it to all the white light. Ghosting, something else to think about. Is the whiteout blanking circuit working correctly? All right, when you think about a digital detector and stuff, if you think back to the CR example that I gave you earlier, remember I said we flashed it with a white light to neutralize the entire plate before we exposed it again. Well, when we got all these little transistors in these detectors, we've got a similar factor in there. We have to flash it. So that helps remove ghosting. If you're seeing double images, you need to start possibly thinking about, is that blinking or flashing circuit working correctly? The iris opening and closing. The iris typically presets in the fluoro mode off the initial pulse. It's not something that's opening and closing all the time. But can it adjust? Because That's an important factor because that first pulse may be at different levels and stuff. So something we should be verifying, does our iris open and close with that? And of course, the auto KV circuit, and we talked about this earlier. All right, as the light intensity changes, this is what adjusts our KV, photodiode array. All right, in our modern circuits. Quickest way for you, put some different density and different thickness objects in the beam, work it through. It should be responding very, very quickly. If it's too much of a delay, this is an indicator that possibly your sensor, your photodiode array, or your photomultiplier tube may be going bad. In our radiographic digital imaging, some things for you to consider: cables and connections. Are they secure? What about your bend points, specifically if it's an add-on type of cable? Again, your power supplies, that goes without question. They need to be as accurate as possible. Your fiber optic cables, we do a lot of transmission of our data, of our digital data across the fiber optic cables. These are very easily damaged. One of the quickest ways that you can check is to remove the ends of the cables, put a light on one end and see if it's coming out the other end. It's not 100% exact, but it can sure give you an indication on whether or not your cable is in fact good or not. Detector calibrations. A lot of systems, operators can do these detector calibrations. However, as we know, typically our operators will not do them. My suggestion to you is to do them in conjunction with your semi-annual PMs. Some of our machines today have reminders built in. A suggestion for you, if you're going to do this on a semi-annual basis, would be to set the trigger point for 7 months. This buys you a little bit of time to get your PM done and then reset the 7-month cycle again without flashing a warning that the calibration is overdue and now our operators begin panicking. The other thing that's come about here more recently is wireless digital imaging. Pairing, very important. Now we've got to worry about our Bluetooth pairing and transfer of our data that way. We have to worry about frequency interference. All right. We've also got to worry about our battery life. Are they properly charged? And their life. Suggestion: once a year on an annual PM, or that's where I would recommend changing them. Again, that helps reduce calls. When we look at artifacts here, foreign objects, all right, if they don't move and they're clear as sharp, it's possibly right on the detector. If they move around on different images, maybe a little fuzzy, maybe it's the tube or an alignment issue. When we look at dead pixel artifacts, all right, remap if it's a live array. All right. The reason that remapping is important is because if the software knows a pixel is bad, it will then look at the 8 surrounding pixels and compensate for that known bad pixel. If it's a CCD camera, unfortunately, mapping is only done at the time of manufacture. And if pixels start going bad, the only thing you can do is replace the camera. Another thing for our viewing is line pair measurements. All right, here you're going to use a special line pair phantom. A little suggestion, especially here in our digital world today, so that we can differentiate on the lines that we're trying to see, is to place them at a 45-degree angle. When we look at our digital detectors, we have columns and rows. By angling the line pair phantom at a 45-degree, you can clearly determine, is that a line from your line pair phantom. Now, I don't care if you view it black on white or white on black, whichever is easiest for your eyes. Our goal is to get the highest lines per millimeter possible. The other thing to consider here is our monitor calibration, the SMPTE pattern. When we look at this, we want to focus on the primary focal of the SMPTE pattern at 5 and 95%. Can we see the 2 squares in each of those areas nice and clear? Again, verify these on PMs. This is going to conclude Film to Digital. I want to thank you for your time.
Perfect, John. Thank you so much. We did have a few questions that came in that we'll see how many we can get through before we hit our 60-minute mark. Attendees, you're welcome to submit questions anytime. If we're not able to get to your question before we wrap up today, I'm going to send it over to John and the Technical Prospects team for them to reach back out to you either this week or next week. But first question, John, is in today's digital world, why do you feel it's important to have a working knowledge or understanding of film principles?
Well, from my standpoint, back in the days of film, the radiographic image to include the processing, we had to do these things very exact because we only had one opportunity to get it right, or it resulted in a retake for the customer. In today's world, in our digital world, we've loosened some of this exactness, and we allow imaging software to make allowances for helping us see what we need to from the radiographic image for the diagnosis. The key thing here is, while the media may have changed, the influences on the image haven't. So the understanding of got to get it right once with a little loosening, we've got to really understand film to really understand our digital world. That's just my belief.
That's great. To build off of that, what do you feel is important for the FE to stay on top of?
Well, in our digital world today, I would focus on both map files and the detector calibration. Make sure they're current and make sure they're accurate. The reason being is the current processing software needs this information in order to most accurately compile the image that we're going to be looking at for diagnosis.
Great. I have an attendee that is sharing a scenario that they're working through. We are replacing some systems and are going from CR to DR plates. We are quoted different prices for CR and DR Bucky cabinets. What is the difference?
Okay. DR is actually using a detector. CR is using the cassette in a reader. That is the biggest difference. Both are digital. CR can be used on an older film-based system. Digital upgrades will turn it into a full digital system only from that standpoint. Again, you can have fixed detectors, you can have add-on detectors, and you can have portable detectors. But the biggest difference there is one is full digital and the other is the kind of the stopgap between the old analog world and the full digital world, that being CR. I hope that answers that person's question.
I love it. Great answer from me. We're going to see if we can get through one more before we hit 3 o'clock Eastern, but does 4K matter as much as it's being touted? And can films be truly printed in an A4 size accurately with dark and light features to use for diagnostics?
Okay, Jamie, could you repeat that question for me?
Absolutely. Oh, I think that's an A4 at the beginning. Okay. Does A4 matter as much as it's being touted? And can films be truly printed in an A4 size accurately with dark and light features to use for diagnostics?
Okay, the machine A4 is more of an international standard as opposed to the stateside standards of 8x11 and things of this nature. Machines will be preset up ahead of time for the different calibration sizes and stuff. I do not believe it's going to make that much of a difference. However, because we're talking in a digital world today, more and more of that film imaging is being discounted, except for like some certification requirements. More and more of this is taking the actual digital file, placing them on CDs to be sent to your certification body. We're sending digital files electronically to different places today. We're reducing that need for printing of all these different images and still maintain the quality of the image due to other ways of transporting that digital image.
Fantastic, John. Thank you for your time today. I always enjoy your presentations, and I want to give a big thank you to Technical Prospects. Again, if you'd like to learn more about this company, please visit their website, technicalprospects.com. Always, one lucky attendee has a chance to win an Amazon gift card for completing the post-webinar survey. This survey will appear on your screen shortly after we wrap up today. Yes, you do have to complete the survey to obtain your certificate of attendance. And if you do not see the survey, please email us at webinar@mdpublishing.com. Just a reminder that Webinar Wednesday is going to take a break next week, but we will return the last week of November with 3 more webinars before we wrap up 2017. You can find out more information and register for the last 3 webinars of this year by visiting technation.com/webinars. Enjoy the rest of your Wednesday. We'll see you back in 2 weeks.